I frequently get the question, FlowJo, which software bundle do you recommend that I use for running a thermal analysis in SolidWorks? There's the thermal tool in Simulation Professional, but I also know that CFD handles heat transfer, so I could use flow simulation. I'm not sure what's best, and I want to make the right choice. Now, that's a good question, and it's not one that's easy to answer. There's a lot of factors that can go into it, such as what level of detail you're looking to get out of the problem, what are some of the objectives, and what are some of the assumptions that you can make. So, again, it's not a really easy question to answer, but I'm going to head off to my local bakery here and I'm going to see what they're cooking to see whether I can get some clues to help answer this question. Okay? So follow me and let's come along. So when I arrive at the bakery, I see that they have a camera set up right in front of the oven, recording what they're baking inside there. So you can see the effect of the temperature in the oven with the rising of the bread and the pan expanding out. I just kept on watching that over and over again because it was so interesting. And you can rewind the video to watch that if you want more times. But let's take a look at the thermal analysis capabilities in SOLIDWORKS and how we can recreate that. So what I did is I set up my own SOLIDWORKS bakery with this virtual oven model that I had set up. So this is an electric convective oven where I'm baking some muffins in there in the aluminum pans. So before we dive into SOLIDWORKS and look more in depth in that problem, we first need to discuss the different types of heat transfer and how they have effect on this. So an easy way to remember this is think of earth, wind, and fire. Okay, those correspond to the three modes of heat transfer. Earth to conduction, wind to convection, and fire to radiation. So we're going to dive into each one of these individually and discuss the attributes of each one. So before I get started, I just wanted to clear up any misconception about temperature because it is a state. It's a measure of how much internal energy is stored at a given point in a body where you take that measurement. It can be either hot or cold. And heat always flows from hot to cold. So that's important to understand in the discussion that we're going to be talking about. So first, let's take a look at conduction. So here is a simplified equation for conduction in one direction, and it's known as Fourier's law. So as I said before, the heat is flowing from hot temperature to a cold temperature, and it happens along a length for a given cross-sectional area. And the material that the medium has, whether it be a solid or a fluid, has a thermal conductivity denoted by K. So the equation is thermal conductivity times the area divided by the length in which the heat travels, and from hot to cold. Sometimes you might see this equation with a negative sign in the front of it, but that just indicates the direction that the heat flows. So by me rearranging it to have hot minus the cold, that's already handled within that definition there. So again, just this simplified Fourier equation is for a 1D problem, steady state, with no heat generation, and assuming that the thermal conductivity is constant. When we move over to a transient 1D conduction problem, we have the introduction of partial derivatives, which are the small delta term, but that just means that temperature can vary both with time and space. So this is a one-dimensional equation, so we only have x represented here, but we can also do the same by adding the y and z components to this equation similarly. So this is also including a heat generation rate, a volumetric heat generation rate. So what's also important to understand here is that we also have the introduction of two material properties, rho, which is for density, and then Cp, which is for the specific heat. So that is important to understand as well. So from those two parts, the steady and transient equations for conduction, some of the important takeaways from that is about the material properties. So for a steady state problem, we had just thermal conductivity, which was important. And then when we got into the transient, we had both density and specific heat. And here are the given units for all of those equations. So you could go back and check those if you want. If we think about the material properties, though, they can be temperature dependent. So if we take a look at the example aluminum material that I'm using in this oven problem for the muffin pan, you can see how it changes with temperature. So over a range of temperature of about 100 Kelvin, say if we're going from 300 to 400 Kelvin, the thermal conductivity value can vary between about 155 all the way up to close to 180. So that can be a significant difference that you want to take account for. So you want to be able to do that and define it in the software. Now, if the temperature difference was much smaller, say between 300 and 340 Kelvin, you only have about 5 watts per meter Kelvin difference in the thermal conductivity. So, that could be assumed to be constant for a small range of values. So if the temperature range is large, the temperature dependency of the material can be significant, so you want to include that. And for most of the time, materials, you can assume that they have the same material properties in the X, Y, and Z direction, but some of your engineered or composite materials can have directional dependency, where they vary in those 3 directions. So you want to also be able to know how to define that within the software. So now if we move on to convection, convection is done by transferring the heat to the surrounding fluid. And in the depiction that I show here, the space heater, this is showing a natural convection problem. So heat rises due to the buoyancy of the fluid and change of density due to temperature. And then when it comes into contact with the surrounding fluid, which is cooler, it falls back down, and then that replaces the air, which is heating up and rising. So that is all done and driven by gravity. If we make the assumption that the surface temperature is constant and the surface area is constant, convection can be defined by this equation you see here. And this is defined by Newton's law of cooling, which describes that H, which is the convective heat transfer coefficient, times the surface area times the change in temperature between the surface and the surrounding fluid. So that defines the heat flow. The conditions for this equation is that, as stated before, uniform surface temperature is a steady state problem, and we assume that the heat transfer coefficient H is constant. So when we move over to the transient convection problem, we see that we have the introduction again of those material properties, density and specific heat, and we have a volume defined by V there. And I just want to point out the units for the heat transfer coefficient in watts per meter square Kelvin. And this equation also, the way that it's defined, surface temperature only varies over time. And H, the heat transfer coefficient, is again constant. So when we look in the details of the mechanism of convection, there are 2 types. One is the natural free convection, which is driven by buoyancy, which I was talking about earlier with the space heater example. And then there's the other type, which is called forced convection, which is a driven flow, either by a fan or wind or some other mechanism like that. So if you take a look at any textbook that is talking about convection, it very quickly gets into a discussion about fluid dynamics, because H can vary based on many factors, some of which are orientation, velocity, the solid material, the temperature difference between the solid and fluid, the fluid type, the shape of the geometry, and its surface condition. So just taking a look at a table of the range of values that this might be, you can see in the first column the medium, so that can be different fluid types, as well as whether it's natural or forced convection. So for air, a natural convection problem ranges somewhere between 5 to 25 watts per meter squared Kelvin, and then the same fluid, air in a forced convection, could range anywhere between 20 to 300 watts per meter square Kelvin. So that can be like an order of magnitude in difference. And then you have the difference between different fluid types. Air versus water. Water, which is a better conductor of heat, can be more effective in removing the heat from say, a forced convection problem at 300 to 6,000 watts per meter square Kelvin. All right, depending on, say, the velocity of the water moving. So then the last heat transfer mode is radiation. So if you take a look at these two images at the bottom, these are thermographs from a FLIR camera, which shows the temperature scale here. The one on the right goes from 8.8 to 153 degrees Celsius. And the white hot shows where those heating elements are, and then the cooler blue is around there. And then similarly, you can see a picture of a car, which this person is working on, and the heat coming from the hot engine there, and then from the person's face and the wheels that picked up heat from the braking. So this describes the mechanism in which radiation works. Because any body which is above absolute zero, that's 0 Kelvin, emits thermal energy in the form of electromagnetic waves by photons. So that means that it can happen both terrestrially, but also in space, which is in a vacuum. All right, so it doesn't need a medium to transfer it like conduction does with a solid or fluid, or convection does with the surrounding external fluid. So first we can have a part which is glowing red hot, emanating heat out to its environment. And that's a surface to ambient radiation condition, which is described by the equation on the screen for a gray body. So what we have is sigma, which is the Stefan Boltzmann constant given by the quantity approximately 5.67 times 10 to the minus 8 times the Greek letter epsilon, which is emissivity, which I'll talk about in a little bit more detail in a second, times the surface area, times the quantity temperature of the surface raised to the fourth power minus the temperature of the ambient condition raised to the fourth power. So it's important to note that those should be absolute temperatures such as Kelvin to use this equation properly. So let's take a look at emissivity here, which is defined by the ratio of radiation which is emitted by a surface to that of a black body at the same temperature. So emissivity is a value between 0 and 1, and it is unitless because the units cancel out one another. And so it would be 0 if the body was a white body, and it would be 1 if the body is a black body. Now those exactly don't exist in nature. Such as, for example, a black body is a perfect emitter and absorption of radiation. The only thing that we know that closely resembles that is the sun, but that's also not a perfect black body. And by Kirchhoff's law, we know that emissivity is also equal to absorptivity, denoted by alpha. And so then that's important to know because this equation can either be described for when the body is emanating or removing heat, so trying to cool down, or when, for like a solar radiation problem, when it's beating down on something, it's defining how radiation is absorbed. We can also have radiation between two bodies, which is called surface-to-surface radiation, so which is defined by the equation you see on the screen for two gray opaque bodies, where it's moving from body 1 to body 2, and you see all the same quantities except for the introduction of F, which is the view factor. So the view factor is a purely geometric value which defines how much one body can see another. So it depends on the shape of the surfaces and the relative orientation of the surfaces and the distance between those. It also can, describe a convex and a concave condition, where in a concave condition you can have a body radiating to itself. And again, the view factor is a unitless value that varies between 0 and 1. 0 being where the surfaces are perpendicular to one another, and 1 is where you have infinite planes which are parallel to one another. Now there's two additional considerations that we need to make for thermal analysis. And the first is thermal contact resistance. That is because truly smooth surfaces don't exist. When two parts come into contact with one another, there are still small gaps in which air can get in between there, and it retards the flow of heat between those parts. And so you can have the thermal resistance depend on a lot of different factors, whether it's just air or there's some interstitial material between those, like thermal grease. But what it primarily depends on is the applied pressure that is pushing the two parts together. And that's the reason why, if you've ever put a computer together, that when you smear the thermal grease onto the heatsink and place it onto the CPU, then you clamp that down, and that applies a pressure for the heatsink and the CPU to have a good contact. The second consideration is when you move to a transient thermal analysis, you can have a thermostat, just like the thermostat you would have in your house to control your HVAC unit. That defines that a heat source can be turned on or off based on a set temperature range for a given selected control point. And because the system might be slow to respond to the change in heat source, you might have a slight overshoot from the target temperature range, depicted in this graph here at the bottom of the screen. So bringing this all together, I want you to imagine yourself sitting around this fire pit on a nice cool evening with some of your friends, thinking about the different types of heat transfer which is occurring around you. So first you have the conduction within the solid benches, which is trying to equalize the temperature by moving those around within the solid. We have convection currents, which is occurring because of the air close to the fire heating up and rising and then coming into contact with the cool surrounding air and then falling back down and creating these convection currents. And then we have the radiation of the hot fire and those stones which are heating up, and you can see how the effect of those, where you have the red glow on the red benches in which it's radiating the heat and keeping everyone warm. So these heat transfer methods are all happening at the same time. And prior to the 1960s, though, they were trying to solve this problem by doing these all separately. And that didn't lead to the most accurate solution. So they started investigating doing a coupled mode of heat transfer between the solid fluids using a combination of methods. And that's what is defined as a conjugate heat transfer problem. Depending on where you're looking at, you can have a combination of any one of these, conduction, convection, and radiation occurring. Which now brings us back to our SOLIDWORKS bakery oven model. So let's go into the software and take a look at this in more detail, where I have both the SOLIDWORKS simulation FEA tool and the SOLIDWORKS flow simulation CFD tool added into SOLIDWORKS. And first I'm going to take a look at the FEA problem. And so I have a new configuration set up for this, where I'm going to assume that the two sides are going to be equivalent. So I'm going to utilize symmetry within this problem. And I've set up a new study type, selecting thermal from that list. And when I go into the properties of the study, I set this as a transient problem rather than the default steady state, and set my total time to be 1200 seconds or 20 minutes. And my time increment for the solution to be 10 seconds. All right. I have additional options of setting the initial time temperatures from the thermal study if I select it from here, or I can include some flow effects from SOLIDWORKS flow simulation. So then we get into the material properties of these parts, and the aluminum pan, which this was defined in the SOLIDWORKS model, so it automatically came over. And for a thermal analysis, you can see the ones that are colored in red and blue are required for this type of analysis: the density, thermal conductivity, and specific heat. And you'll notice that for thermal conductivity, I have this defined as with temperature-dependent properties, which you can access that by just selecting in the value box here and then choosing that from the list below here. So if I wanted to set specific heat with the temperature dependency, I could do that. But let's go here and see how I define that for thermal conductivity. And just taking two columns of data that I had from an Excel spreadsheet, I just simply copied and pasted that into here, these two columns. And then this is the image that I showed you earlier on in the presentation. So going back to the properties of the study here, You can also note that we can define these properties with orthotropic material properties so that they change in X, Y, and Z directions. Then I define a custom material property for the muffins. And then the oven, both for the heating element and for the rack, I have defined as a plain carbon steel, which are default from the SOLIDWORKS material library. I didn't set any thermal contact resistance for the materials, but you can define that through this interface here, selecting the bodies which are, you're going to define that thermal contact resistance and setting the value either as a total or distributed value with its corresponding resistance quantity with the unit of Kelvin over watts. All right, so with a transient solution, first we need to make sure that all the parts have an initial temperature defined. So when the muffins and the pan are placed into the oven, they're at room temperature, 70 degrees Fahrenheit. The oven is preheated to 350, and then we're going to be setting the heating element throughout the entire calculation to be 1200 degrees Fahrenheit. Since we need to define the convection coefficient in an FEA problem, because we can't solve the fluid dynamics problem, we're going to define that with a specified unit of 8 watts per meter squared Kelvin with an ambient surrounding temperature of 350 degrees Fahrenheit, which is within the oven. And you can see how I can change between the units just by choosing that option there. And I did the same thing for both the oven and oven rack and the heating element. And then I set the radiation values for the heating element, which is a nichrome material with a emissivity of 1, and the aluminum pan with an emissivity of 0.75. I also want to note that symmetry for a thermal analysis problem is such as where the part is cut here, here, and here. I have no conditions defined for those because the symmetry condition is that it's perfectly insulated, and by defining no condition, that means that that's a symmetry condition. So then we can take a look at the results, and the total time for this to solve was just over 5 hours. And I can tell you that the majority of the time that it took to solve is in doing the view factor calculation between the heating element and the aluminum pans. And that's a lot of each surface of an element needs to find out what the view factor for every other element surface, which is included within this study, so that there's a lot of geometric features that it needs to look at, as you can see with the mesh. So let's take a look at the results here. And the first thing that you'll notice is that the temperatures are ranging from 1200 degrees Fahrenheit down to 110. It's being dominated by that heating element. But we can cut that back down just by, if we isolate the muffins in the pan, and then we hide and reshow this plot, then the legend is corresponding just to what is shown on the screen. And looking at this, and what you notice right away is that each of the muffins is almost exactly the same, all right? And if we also take a look at a section clipping here inside this muffin for the last time step, 120, is that they are very uniform in nature. Okay, the results are very cylindrical for a given muffin, and that's all due to the way that we've set up the problem with it. equivalent convection coefficient for all of the surfaces of the body. And that's just based on it being simple to define it like that with no additional information, right? So when we define the convection coefficient, we take the lazy man's way out and just choose all the selected exposed faces, and then we give it a corresponding convection coefficient value, all right? So that kind of defines how you can do a thermal problem in Simulation Professional in our FEA tool in SOLIDWORKS Simulation Professional. So let's move back to our full configuration here and take a look at the solution if we were going to do it with flow simulation. All right, so what I did was first an interesting pre-step to running a transient analysis is I preheated the oven. So I'll actually go to that configuration first, and you'll see that I removed the muffins because you have the heat going on. So this is a convective oven, so I defined a fan here, as well as the temperature of the nichrome heating element. And when I define this heating element is 1200 degrees Fahrenheit, and I specified a point just where the sensor for the thermostat would be, and I defined for this calculation to finish, if we zoom in here, when that point got above a temperature of 350 degrees Fahrenheit. So if I load in these results and then take a look at the solution, we can take a look at a goal plot for that point and see that after the steady state solution got to a temperature of 350 degrees Fahrenheit, it stopped the calculation and that we have the oven preheated. So then we can move on to where we add the muffins into the oven. And in the setup of this problem, we have conduction, and radiation, as well as gravity to define the convective buoyancy effect. But I wanted to point out here the initial condition is defined by transferring the values from that flow simulation project that I just showed you, where we preheated the oven. So everything is at a nice toasty 350 degrees Fahrenheit inside the oven there. So for the materials, we have an insulating foam for the back. We have nichrome for the heating elements. We have aluminum for the baking pans. We have a glass front to see inside the oven. And then the steel rack, and then the muffins are that custom material. So let's take a look at the aluminum material and how that's defined in this flow simulation. So we can take a look at the density as a constant value, but the specific heat and thermal conductivity have temperature-dependent properties. As I mentioned before, we have a fan, which is blowing air to circulate the air and equalize it out. And this is defined by a fan curve, as you can see here, flow rate versus pressure drop. We have our heat source as a temperature here, and because this is a transient analysis, we can define a thermostat condition where after it's reached 350 as a control value, it can turn off, and there's a dead band of 2 degrees Fahrenheit. So the temperature is set at 1200 and then turns on and off with the thermostat based on that point in the back here, located as I showed you earlier. We have radiative surfaces for the nichrome and the rack. Those are the same as I showed in the FEA. Nichrome is 1, and the rack and the pans are 0.75. And then we have the initial conditions of the muffins and the pan at 70 degrees Fahrenheit. So then we can take a look at our results. I'm going to collapse down our input data and expand the results. And first we can take a look at the flow trajectories, because this is different from what we saw in the FEA solution. So we have the velocity of the air inside the oven moving around based on the fan. You can see that the fan is coming in here, swirling around. And so these colors are showing the velocity, but we can also change this to the temperature of the fluid. Right, and if I show a cut plot, so this is also showing the temperature inside the oven of the fluid, and it has a high temperature around where the heating element is. And I can use my probe tool to probe anywhere around here and find out exactly what the temperature is. Okay. Also, I can edit this and change the location just by sliding this arrow here, and then again probing in those locations all around here. Next, let's take a look at the surface plot of temperature for the muffins and the pan. And let me hide this flow trajectories here. So what you notice with this and how it differs from the results from the FEA is that they are not uniform, right? We have some hotter temperatures in this corner versus the temperatures in this corner here. And the way that these muffin pans are placed in here is not exactly uniform from left to right either. And we can take a look at this in a section type of view, showing like this. If I make the entire model transparent, so we can see through and see what's going on there. And if I'm interested in a specific point, I can drop that point there. Now, the main difference in the results is how the convective heat transfer part of this is handled. And in this flow simulation, we're actually solving for the convective heat transfer value, which I can show you here by selecting it from this list of parameters that I can show. And so you can see that the range is between 1 and 26. And there's a lot of local variation where you have some higher values here and then some lower values where the velocity is maybe lower, or the temperature of the fluid is higher, right? And over here, this is the difference between the left and the right side. You have a higher heat transfer coefficient on the right, meaning that it's more effective in the convective heat transfer. Again, I'll show the heat transfer inside the oven with the flow trajectories playing here. And this really gives you a good description of the heat transfer. So let's take a look at the animations from the FEA solution and then the CFD solution in their thermal analysis transient results. And finishing this up, let's do a comparison of the thermal analysis tools to answer our question. So let's take a look at the thermal module in SOLIDWORKS Simulation Professional, and then the heat transfer capabilities in the SOLIDWORKS Flow Simulation software. So I'm going to do this on a 3-point scale: a green check mark for a good job, a yellow dash that does okay job, and a red X where it doesn't work at all. So for conduction, I give them both an equal green mark because they equally do a good job with conduction. But for convection, I'm going to have to give the FEA thermal analysis tool a yellow dash because it does it, but it just does an okay job because you have to know what the heat transfer coefficient is. And what that means then is you typically are defining it on larger over the entire average surface rather than capturing the true localized nature of convection like the SOLIDWORKS flow simulation can do. So I give that one a check plus. And for radiation, again, I'm going to give the FEA tool a check because it handles it, but it takes a really long time to solve. Whereas in the flow simulation, radiation is handled while it's solving and it does it in steps. So you don't have that additional view factor calculation that takes a really long time. In meshing, again, the meshing tool is really nice in the FEA tool, but they're so much easier and better to do in the SOLIDWORKS flow simulation. And I know I didn't have a chance to get into that in too much detail, but you have to go by my own recommendation on that one. And then for solving and the results, again, I'm just going to give a check mark to the thermal analysis. The SOLIDWORKS flow simulation does a much better job in visualizing the results and doing animations and things like that. Again, I just have to give this a check plus. So just visually, if you compare these, heat transfer capabilities in flow simulation gives you a much more complete thermal analysis solution than you have with the FEA tool in SOLIDWORKS Simulation Professional. So it depends on what your needs are, and if you can make certain assumptions, then the thermal analysis tool is fine. But if you want a complete thermal analysis package, SOLIDWORKS Flow Simulation is your solution.
Yum. Now that's good work.